In the previous videos, we saw that for a lot of operations like direct sums, tensor products, kernels, and images of quasi-coherent sheaves, the result is again quasi-coherent. But there was a very simple operation, namely the push forward, which we haven't discussed. And in fact, it's not true in general that the push forward of a quasi-coherent sheaf is quasi-coherent. So this doesn't hold for arbitrary morphisms, but it's hard to construct counterexamples, and for the rest of the course, this will not really be relevant. There is an important case where push forwards behave nicely with quasi-coherent sheaves, and this is if we push forward under the embedding of a closed subscheme. And this leads to an interesting exact sequence, and this is what the next lemma is about. So assume that you have a closed subscheme Y inside X, then the first part says is if F is quasi-coherent on Y, then if you push it forward, you also get a quasi-coherent sheaf on X. And moreover, then we get an exact sequence. So from this morphism in general, we always have this map here from OX to I push forward OY, which is part of the data of the morphism. And the claim here is this map is surjective. So we can extend it like this, get an exact sequence. And then we can define its kernel to be a certain sheaf J Y over X. And this will be called the ideal sheaf of Y inside X. And it is again a quasi-coherent sheaf. And what you should think of this J Y over X, it sits inside this OX, and this is injective. So on each open set, actually, the sections here sit inside the regular functions on here. And you should just think on this open set, the sections here are just the functions on U which restrict to 0 on this closed subscheme. This is why it's called an ideal sheaf. On every open set, it gives you the ideal of functions vanishing on the closed subscheme. Okay. And so for the proof, so first we have to show this is quasi-coherent on X. And we start with the assumption that X itself is affine. Because then, this we mentioned, then a closed scheme of an affine scheme is actually one of these closed affine schemes that we have seen. So this Y is actually of the form spec R modulo I sitting inside by this I in spec R. So it comes from the surjection from R going to R modulo I to this quotient. And so if F is quasi-coherent on Y by definition, so somehow since this is now also affine, we see that it must come from a full module on over the ring R modulo I. So somehow this F is equal to M tilde for an R modulo I module M. And so this is kind of the starting situation if we reduce to the affine case. And now we just need to understand what is the push forward. And we need to identify it as a certain module over here. So coming from this module, this would show it's actually quasi-coherent on there. And well, we have a module around, and then we just do a trick here, namely via this map R to R modulo I, we can actually see this M, which is an R modulo I module, as an R module. And we write MR to emphasize this. So this MR as an abelian group, it's exactly M. The only thing which changes is now we can multiply, if we want to multiply an element in M by any element in R, what we just do is we first take the image of that scalar in R modulo I, and then, since M is an R modulo I module, we know how to multiply. So this is kind of just changing the coordinate or changing the base ring of this module. And so, well, we did get our hands on an R module, and so we also get the associated sheaf on spec R. And the claim is this is the sheaf that we want. So this I push forward F that we want to show is quasi-coherent. This is just MR tilde. That would prove the statement, and it would also show us how do you actually do the push forward on, at least on this affine situation. You just take the module that you start with and interpret it as a module over the target train. To do this, so now always when we want to show some modules are sheaves of modules are the same, we look at the stalks. And so the stalks of this R module, this is just a lemma from commutative algebra. They come in two forms. If you take the stalk at the point in spec R, which actually lies inside this closed subscheme Y, so if P is in Y, then the stalk is just, well, take this this prime ideal P times R modulo I. This is a prime ideal in R modulo I, and take the stalk of M, or the localization of M at this point. This here is, of course, also equivalent to P containing I. And otherwise, if you're away from Y, then the stalk is just 0. And this now allows us to prove in a second that these two modules have the same sections on any open set of X of spec R. So, namely, we can say on U inside X open, we get a map. So this is always, we first get our hands on the map from one side to the other, and then we show it's an isomorphism. So the nice direction here is we can, for example, take this. And then we have this MR tilde on U. And now, what does this here mean? What is the data of having a section here? Well, by definition, it's just a section of F on I inverse of U. And sorry. It's just a section of F on I inverse of U. And this means that for all points inside, so for P in I inverse U, we just have the data of some elements of these stalks. So the stalks are at this P times R modulo I, and they need to locally be a quotient. This is this compatibility condition. And this thing gets sent to now the sections here, where for any P in U, we need to write down something in the stalk of MR, which we have just calculated. And so somehow, let's just call it like this for now. And then this element here, we just distinguish these two cases. If P is in U intersected Y, then we can just take this thing here. This lives in here, and this is the same as this. So somehow we just say this is by P if P is in U intersected Y, and otherwise this thing is already 0, as we see here. So we just define it as 0. And okay, this is our definition. And you check it is well defined, and then you can actually see this is an isomorphism. For example, I mean, writing down the inverse, you just see any section here. Well, you have exactly this data, and then the zeros don't really matter, and you just get the data of these elements here, and then you just send it right back to this. And so you can verify for yourself this is an isomorphism, which proves this thing here. So this means that when X is affine, then actually this push forward is a quasi-coherent sheaf. And if X is general, well, what will we do? We just cover X by some affines. and apply the first part. Because then the idea is we can calculate the push forward locally on a cover of the target, and then the cover of the target are the spec Ri. And we can also verify that some sheaf is quasi-coherent on an open cover of the target, and then all the check just reduced to working on this affine cover, and this we already completed. So that's good. So this part is fine. And then for the second part, so if you recall, we have proven it's quasi-coherent. Now we want to have this exact sequence. And in this exact sequence, this part here is kind of true by definition. So somehow, if you have a morphism, then the kernel of this morphism is always injective, which you can check on the on an open cover or on the set of all open subsets. So this part is always exact here, and by definition exact here, because somehow this is defined as the kernel. So somehow the image of this is the kernel here. So this is also fine. The only exactness that we need to show is here. So in other words, we need to show that this here is a surjection. And again, we can do this now on an open cover. So let me just write what I said at the beginning. So somehow this J, Y, X is defined as the kernel. And so this proves exactness at these two places, left and the middle. And so we only need to check that this OX going to I push forward OY is surjective. Okay. And we have seen that we can check surjectivity. So this was a lemma 13.21 in the script. Surjectivity can be checked on an affine open cover. Basically, because surjectivity can be checked at stalks, and stalks only depend on an open neighborhood. And so we can just assume from the start here, assume that X is equal to spec R. So we're back in this nice situation. And then we can actually check the surjectivity on the module level. This is exactly what we're going to do. So we want to check this OX going to I push forward of OY is surjective. And now we know, so somehow we are exactly in this situation, X is spec R and Y is, so somehow we can also assume here Y is equal to the spec R modulo I. And so the structure sheaves on X and Y come exactly from the modules R and R modulo I, as we have seen. So this is R tilde, and this is R modulo I tilde. And so this is given by now a map. So somehow this push forward we have seen in the proof just now is obtained by just taking this module here, R modulo I, and seeing it as an R module. And so, and then this map here is just given by this R tilde going to R modulo I tilde, where we see the R modulo I as an R module. And now we're in good shape because now the map of sheaves that we're interested in comes from a map of R modules, namely just the map going R mapping to R modulo I. And so we just observed that, of course, R going to R modulo I is surjective. And so we get an exact sequence. 0 goes to I goes to R goes to R modulo I goes to 0. This is exact sequence of R modules. And then the corresponding sequence of sheaves is also exact. And this was this lemma 14.7b. And so this just means we make a twiddle over all things here. This is exact. And then, I mean, this being exact just means that this thing here is surjective. And this is what we wanted to show. So this completes the proof. And in fact, we show a bit more here than we wanted. Namely, from this exact sequence, remember, the J is defined as the kernel of this map. And so it is actually just given by this I tilde, right? So somehow if we are in this situation, then J is just I tilde. So we recover this, the ideal sheaf just comes from, well, the actual ideal I that we divide out. And so as an application, we can now revisit some of the exact sequences that we did by hand before. So for example, if you have this point 1, 0 inside P1, and you have this inclusion in P1 and the usual cover by affines, then we saw that if you push forward this O of P, then you get exactly this skyscraper sheaf at the point P. And then we had a skyscraper exact sequence. So somehow this goes from OX to KP. And the kernel we saw was O minus 1. But then now we can reinterpret this. We know that this map from OX to KP, this is just the map from OX to I push forward OY. And this we have seen, we can have kind of reproved that it's surjective at this place. And we defined the kernel sheaf to be the kernel to be the ideal sheaf of P inside P1. And because the kernel is unique and we have already seen it's O of minus 1, this actually shows that the ideal sheaf of a single point inside P1 is just O minus 1. And it also shows that this skyscraper sheaf, which we defined by hand, is in fact quasi-coherent. We can check this on this open cover, because the claim is that on U0, it is given exactly by the module associated to, or this module given by kx1 modulo x1. This is a module over the ring kx1, whose spectrum gives U0. And then on U1, which is exactly the complement of P, the skyscraper sheaf is 0 everywhere, and in particular it's the sheaf associated to the 0 module. And we can reprove this exactness using these quasi-coherent sheaves, because on U0 and U1, this sequence here exactly restricts to these sequences here. So somehow this module sits inside there. And then, I mean, we had seen how this map from here to there goes, because it's basically just this kind of multiplication by x1. So I don't want to go through all of the details here. It's something that you should look at yourself, but somehow let me just say that in Gutmann's script, he uses these affine coordinates and then mentions that this is the sequence of modules, which gives this sequence of sheaves on the two covers. And you can actually also just directly go to the definition of O minus 1 and OX, and then see that the sections of these on U0 and U1 are exactly given by these modules here, and the maps is always multiplication by x1. And I found this presentation here a bit nicer to understand. So you can have a look for yourself. And the upshot is here that we can recover this exactness that we did kind of by hand before, we can recover it from the ideal sequence that we just proved. Okay, so this was this, and let me just conclude this video by saying a bit more about ideal sheaves in general, because these are actually really useful, in particular for further constructions like this. So by definition, an ideal sheaf is just an OX module J together with an injective map from J into OX. And the lemma that we had above shows that if you have a closed subscheme, then it's this kernel of this map which we defined is an ideal sheaf because it sits inside OX in an injective way. But there's also a converse, namely, if you have an ideal sheaf which is also quasi-coherent, then this determines a closed subscheme which has exactly this as an ideal sheaf. So you can define the vanishing locus of this ideal sheaf, and this sits inside there as a closed subscheme. And the idea is, again, we go to an affine cover. So somehow if the spec Ri cover X, then if you restrict this J to the spec Ri, then by definition, it must come from some module, Ji, which sits injectively in this Ri. And somehow being an Ri module, which sits inside Ri, this you can immediately check is equivalent to being an ideal. So this Ji is actually an ideal inside Ri. And so at least on this open cover, you get this spec Ri modulo Ji sitting inside spec R as a closed subscheme. And then as these things cover all of X, you get these closed subschemes in each part. And if you glue them together, you exactly get this closed subscheme Y inside X. So there's a one-to-one correspondence between closed subschemes and ideal sheaves, which is nice because somehow there's also one-to-one correspondence between closed subschemes in an affine scheme spec R and the ideals I inside R. So this basically gives you a way to think about closed subschemes. Also, we can then finally make the most general possible version of blowups, namely, if you have J, a quasi-coherent ideal sheaf on a variety X, then you can actually define what it means to blow up this ideal sheaf. And again, well, always the same trick. You go to an affine open cover, then on there, J restricts to some ideal, or the sheaf of modules coming from an ideal inside A of U. And then we did define what it means if you have an affine variety, you have an ideal in its coordinate ring, what it means to blow up this ideal. And then these things glue together, and then you get the blow up of this ideal sheaf inside X. And this is the most general version of blowing something up inside such a variety. And then finally, maybe as a more interesting example of ideal sheaves, if you have X inside Pn, an irreducible hypersurface of degree D, then this is a closed subscheme here, and you can show in this exercise that its ideal sheaf is exactly O of minus D. If you want to prove it, you should first look again at this case of the skyscraper sheaf, and then try to generalize, like, how does this O of minus D, for example, map into OPN, because it should sit inside here by an injective map, and so on. So you see somehow the degree of the hypersurface exactly tells you which of these twisting sheaves gives the ideal sheaf. Okay, so this was everything about these ideal sheaves. And so we have seen the quasi-coherent sheaves are really useful because you can check everything on the module level. And so from now on, all sheaves on a scheme are assumed to be quasi-coherent. And then we learn a bit more about these in the final videos of this chapter.